First keynote, I'm so sorry, is Professor Sergey Levine. So Sergey is a professor in the ECS department at the University of California, Berkeley. Sergey has been a really important driver of methodological developments in robotics and machine learning, reinforcement learning, including more recently the integration of deep learning methods, and also ways of efficiently learning from offline data or unlabeled data. The focus of their research is on developing algorithms that enable autonomous agents to acquire complex behaviors through general purpose means. And that's probably the most on-topic self-description I've heard for this summit, and we're very excited to hear from Sergey today. So if we could welcome him, and let's get ready for the talk.
Great, thank you for the introduction. All right, so today I'm going to talk about how decision-making and data can be combined to give us resourceful and capable autonomous agents. Let's start with kind of a big picture thought exercise. Let's say that we needed to build an AI system to control a robot that's going to go and explore another planet. It's a very open-ended problem for it to solve. Now, some of the things this robot is going to encounter are familiar, some of them are unfamiliar, and the whole point is that you don't know exactly what you're going to meet until you actually go there. This is very much analogous to the problem of a person who's stranded on a desert island and has to use all their resourcefulness to fend for themselves. There are a lot of things that they bring from their prior knowledge. There are also a lot of things that they need to discover, novel solutions to novel problems in the situation that they find themselves in. So what can we glean from recent advances in AI that would allow us to tackle this problem of building this planetary exploration robot? What are the big advances in AI that we can draw on? Well, maybe two big categories of advances that we've seen over the last decade have been in data-driven AI methods like generative AI, as well as reinforcement learning methods. And these are very different, and they bring very different capabilities to the table. So probably the one that's on a lot of people's minds is the category of generative AI methods. These are things like image generation models, language models. They can do some pretty amazing things. They can generate pictures that look just like things that a person might draw. They can generate text that looks like something a person might say. They can have a conversation with you. They can solve problems. Fundamentally, however, these techniques are all about looking at large amounts of data and modeling the distribution of the training data they're provided with. So in introductory statistics, we learn about basic techniques like density estimation. That is essentially what these techniques are doing, just scaled up massively and trained on very, very large data sets. And what that means is that they're trying to represent the distribution of either text on the internet or the distribution of images given particular textual labels. And the kind of problems that they solved are basically determined by how people chose to put data on the web. So people chose to take certain kinds of photographs. That's the distribution of images. People chose to type certain things on keyboards. That's the distribution of text. Now, of course, there's a lot more that goes into this. In reality, actually fine-tuning these models in various ways to get them to perform certain things more deliberately is a major research area. But deep down, what these models are doing is replicating the distribution of things that they've seen in training. And then, of course, it's not surprising to see that they produce very human-like outputs because, well, they're trained on data from humans. What does reinforcement learning do? Reinforcement learning is solving seemingly a very different kind of problem. And reinforcement learning is about having an agent that interacts with the world, examines that interaction, and modifies its behavior in response to what it saw. Reinforcement learning is an iterative procedure for optimizing a behavior to maximize some utility, to maximize some reward. Reinforcement learning techniques have been very effective in a range of domains, from playing video games to robotic control to even playing the game of Go. Reinforcement learning methods can lead to very interesting emergent behavior. AlphaGo was impressive not because it played the way that a human would play, but because of things like Move 37, where it discovered a move that surprised even human experts. This emergent behavior in reinforcement learning is one of the things that was actually very inspiring to a lot of people because it suggested that machines could solve problems better than humans could solve them. In contrast, generative AI techniques are impressive because they generate pictures that look like something that a person might draw. They generate text that look like something a person might write. Reinforcement learning is impressive because it'll generate solutions that no person had thought of. So these are very different things. Now, of course, the way I'm presenting it might make it seem like, oh, reinforcement learning is like the way to go. Why would we ever want anything else? The trouble, of course, is that reinforcement learning techniques really shine in constrained environments with known rules, especially ones that we can simulate in a computer. It becomes very challenging to apply reinforcement learning methods at scale when we have to deal with complex real-world physics, diverse and complicated situations, open world settings, multi-agent interactions, the kinds of things that demand generalization which in turn comes from being able to leverage large data sets. So there's a big gulf with reinforcement learning methods, which is not in their ability to discover better solutions, but in their ability to handle diversity and variability of the kind that data-driven machine learning methods really excel at. And this is because if we want to use this kind of iterative learning procedure with very large data sets, it means that every time the reinforcement learning agent improves its behavior, it has to collect a large and diverse data set of a scale comparable to something like ImageNet, improve its policy using that data, throw that data in the garbage, and then repeat all over again. And this would simply not be practical. So where does that leave us? Well, data-driven AI is really great for learning about the real world from data. You can ingest huge amounts of data from the web, figure out the distribution of images that humans might draw, the distribution of text that humans might write. You can learn a lot about the open world diverse settings. But it doesn't really try to do better than the data. It's not trying to answer your queries in a better way than the smartest human possibly could. It's not trying to beat the world champion in the game of Go. Reinforcement learning optimizes for a goal with emergent behavior. It really goes all out to figure out how to accomplish some objective, and in doing so, it might discover solutions that are better than solutions that humans have discovered before. But in its native formulation, reinforcement learning doesn't make use of real-world data. It doesn't provide us with a means to ingest huge amounts of experience and get superior generalization. And in principle, we would really like to have the best of both. We would like to analyze patterns in very large data sets, but then leverage those patterns to make better decisions than the humans that generated those data sets in the first place. So data-driven AI is all about using data. Reinforcement learning is all about optimization. Data without optimization doesn't allow us to solve new problems in new ways. Whereas optimization without data is hard to apply to the real world outside of simple simulated environments with known and well-codified rules. So, of course, what I'm going to try to talk about today and try to hopefully convince you of is that if we can put together these two disciplines, then we can get much more capable autonomous agents that can solve complex real-world problems, but do so better than the best humans. So here's a notional recipe for our space exploration robot from the beginning. We're going to go explore another planet, but like any good explorer, we'll start by training here at home. We'll start with data sets that we can gather from experience that you can get here on Earth. Maybe experience from other vehicles. Maybe just experience of experiencing the physical world. Things that might not directly pertain to your mission, but kind of teach you about the cause and effect structure you should expect to see in this universe. And we're going to use those data sets with reinforcement learning methods that are different from the traditional iterative reinforcement learning methods. These are going to be offline reinforcement learning methods that reflect on the data that they're provided, use that data to figure out what is possible, and try to, from analyzing it, find better behaviors than the ones that were actually displayed. So instead of using the data as something to imitate, use the data as something to describe the possibilities available to you, and among those possibilities, pick the best ones for the goals that you might have. But of course, we're not done yet. Then we're going to go to the other planet. And when we're there, we're going to use what we learned to hopefully behave intelligently, but also improve from our own experience, such that if a novel situation presents itself, then we'll be able to find a novel solution to this novel situation. And this ability to remain flexible and adaptive, to adapt using our own experience, will give us that flexibility to handle the unknown. So in today's talk, I'm going to tell you about some techniques that perhaps suggest how we might get to this type of notional system at some point in the future. And I'll talk about this central question. What can we accomplish if we combine data and optimization, data-driven ML and reinforcement learning? I'll describe the fundamentals of offline RL. What are the basic mathematical principles that make it work? I'll talk about offline RL for language models and how we can actually combine some of the best of generative AI and the best of reinforcement learning to get more intelligent agents. And then I'll talk about how some of these ideas can lead to robotic foundation models for controlling robots in diverse and varied situations. But let's start with the algorithmic fundamentals. So first, what is this offline RL thing and what do we expect it to do? Well, offline RL is fundamentally about looking at a data set and finding good behaviors that are better than the typical behavior demonstrated in the data set. So one bit of intuition that sometimes gets thrown around that I think is not entirely accurate is that offline RL is a lot like imitation learning. So in imitation learning, you have data that demonstrates how you should perform a task, and your goal is to imitate that data and find a policy, a neural network, that will reproduce similar behavior in similar situations. Offline RL is not really about doing that. It's about taking a more diverse data set and finding better behaviors. So instead of all of your behaviors being consistent like in the picture above, imagine that it looks more like this, a variety of different things that sort of illustrate what you could do in this world. This is a very simple world. It's a world of walking around on a two-dimensional page. But still, from looking at this, you can figure out that, well, maybe this kind of path might be a feasible path available to you, even though no single trajectory in the data set actually showed this. But from looking at what you've seen, you can kind of piece it together and figure out this is something you could do, and that's a better behavior than any of the ones you actually saw in your data set. As a very simple example of this, if you've seen an example of going from A to B and an example of going from B to C, you should be able to figure out that you can go from A to C. It's a very simple inference that you can do by understanding the temporal compositionality in the world. But of course, the real power of these ideas comes when we can do this everywhere all at once. If you have a variety of highly suboptimal behaviors and you can figure out the best piece of each behavior in each situation, you can do much better overall. Imagine that you have data from human drivers driving vehicles, and each human driver is good in some places and bad in others. No one human driver is good everywhere, but if you can synthesize a behavior that is as good as the best human driver in each situation, then that behavior will be better than any single human overall across the board. So that's the basic principle. Now, to try to understand how these principles can be instantiated in an algorithmic framework, we need to go into a little bit of a quick primer on reinforcement learning. So I have only a couple of slides of math. I'll go through this pretty quickly. Those of you that are familiar with some of these machine learning techniques, hopefully this will kind of make sense. If it doesn't make sense, it's OK. I'll come back to kind of the big picture story after that. So in reinforcement learning, we have an agent that interacts with the environment. It selects actions A, and the world responds with states S and the reward R. And our objective is to learn a policy. A policy is just some function that takes in the state and outputs the action, or more generally, a distribution of actions that you should take. And a good policy is one that maximizes the cumulative return, the sum of rewards that you'll experience over all time. So you don't just want the highest reward now, you want the highest reward over the duration of your lifetime or over the duration of your trajectory. A very useful object for solving this maximization problem is something called the Q function. The Q function is a function of your current state and action, and it tells you what is the total reward that you will accumulate if you take that action in that state and then follow your policy until the end. And if you can find the Q function for a given policy, then you can always improve that policy by simply taking the action that is the argmax of the Q function. That makes a lot of sense. If the Q function tells you what's the total reward, we'll take the action that will have the highest total reward afterwards, and that'll get you a better policy. This is the basis of something called policy iteration. You can also short circuit this and instantiate something called Q learning, where you basically substitute the argmax action into the target value in a Bellman backup, and with a little bit of math, you end up with this equation. This is the basis of modern Q learning, DQN, all of those algorithms that everybody has been studying for a while. And it just says that if you can find a Q function that is equal to the current reward plus the max of the Q value at the next state, that will be the optimal Q function, and its greedy policy will be the best possible policy. So what people typically do is they say, like, OK, let's enforce this equation everywhere. Now, in reality, states are continuous, so you don't have all possible states, so you'll have samples. So then you'll minimize the difference between the left-hand side and right-hand side of this thing on your sampled states and actions. Okay, very standard Q learning algorithm. And the interesting thing about this procedure is that it doesn't actually assume that your states and actions came from any particular policy. So it's what's called an off-policy algorithm. And because of this, it's been the starting point for a lot of the study of offline RL in the literature. They say, well, it's an off-policy algorithm. That means that you could use data collected by other behaviors. Let's see if we can make that work. Now, traditionally, the way that these methods are used is that new data is collected online in the loop, added to a replay buffer, and that data as it's being collected is used to update these Q functions. If you take away the data collection process and you want to use this entirely offline, it turns out that you hit a pretty major problem. And interestingly enough, we didn't really understand this problem until maybe about 6, 7 years ago, but it turns out to be fundamental for enabling offline RL to be effective. And the issue is actually weirdly related to something called adversarial examples, which coincidentally also is something that we only learned about as a community within the last decade or so. So the fundamental operation in Q learning, which something like this exists actually in any reinforcement learning algorithm, is some kind of maximization. Your Q function estimates the value you're going to get, and then you want to maximize that Q value with respect to the action. In Q learning, you do it in computing the target values. And this is where all the problems start. So here's how we can see what the problem is. Let's rewrite this in a slightly different form. I'm not changing the equation. I'm just writing it differently. Let's say that this max is the expected value under some distribution pi nu, where pi nu assigns a probability of 1 to the argmax. It's exactly the same equation. Assign probability 1 to the argmax, you get the max. But this equation makes it a little bit more clear what the problem might be. So we have these target values y. We're evaluating our Q function in expectation under some distribution pi nu. If you want to know if your function is accurate in expectation under some distribution, the right question to ask is, well, what distribution was it trained under? If you test under the same distribution that you trained under, you should expect it to be accurate. If not, then you should not expect it to be accurate. Well, the training objective is the difference between the left-hand side and right-hand side of that Bellman equation in expectation under the distribution in the data set. It's sometimes called the behavior policy. That's a little bit of jargon in offline RL, but it's basically the data set. Now, the whole point of running RL is to improve over the typical behavior in the data set. So pi nu is not going to be the same as pi beta, as the data set distribution. The whole point is to find a policy pi nu that is better, which means that by improving the policy, you're introducing distributional shift. You are testing your Q function under a different distribution than you train under. And even worse, pi nu is selected to maximize that Q function. So it is strongly incentivized to fool the Q function and find actions for which the Q function erroneously thinks the values are very high, and then take those actions, and then acquire even higher values. It's very much like adversarial examples. It's injecting actions into this Q function that the Q function erroneously thinks are better than they really are. And in fact, if we measure what happens if we run naive Q learning, well, it doesn't work. So these curves show reward. X-axis is how long you're training. Y-axis is how good the policy is. It's not getting any better. That's bad news. If you look at the Q value, which is its estimate of how well it thinks it's doing, that of course goes up. And the y-axis here is a log scale, so it goes up to like 10 to the 7th power. And in fact, it's getting like minus 250. So that's exactly what you'd expect from adversarial examples, from exploitation. The policy is finding actions that fool the Q function to thinking that it's really good, backs up those actions, repeats, the values go up and up and up, but it doesn't actually get a good outcome. So the problem is distributional shift, which is basically the problem in adversarial examples. So what can we do? Well, there are many different methods for offline RL, but they all share similar principles in that they're addressing this exploitation problem, this distributional shift problem in various ways. At a high level, most modern offline RL methods that are effective use value-based methods, basically Q learning or Q function actor critic. And then they somehow fix this distributional shift problem either through pessimism, which basically, roughly speaking, says if you're not sure what the value should be, assume the value is bad, so that unseen actions don't end up with erroneously high values. They might end up with erroneously low values, but then you won't take those actions. Constraining the policy, basically saying don't let the policy deviate too much from the one that you saw in the behavior. Or some other more exotic tricks like avoiding out-of-distribution actions altogether by basically rewriting the form of the Bellman update. I'll summarize one technique very briefly, and mostly because this one is like fairly intuitive and it works like decently well, called conservative Q learning. But I want to emphasize that there are many techniques for making offline RL work. Conservative Q learning, roughly speaking, tries to address this overestimation issue with methods that are quite similar to adversarial training in spirit. So if the issue is that you fit this, let's say the green curve is the true function, you fit it with this blue curve. The blue curve is accurate almost everywhere, but if you try to maximize it, then you'll find exactly the place where it's most wrong in the positive direction. Well, what you can do is you can just find those places where your fit is very large and just push it down, just minimize it. And that's basically the essence of adversarial training. So this is the equation. It's a little bit complicated, but it actually breaks down to two very simple parts. This is the regular objective, exactly the same thing as before. Bellman equation, left-hand side minus right-hand side, regular Q learning. The only new thing is this thing at the top, where we're finding a distribution mu that maximizes the Q values, and then we're minimizing the Q values under that distribution. Very simple, it just says find those big Q values and make them small. Now, of course, for the Q values for actions that are in distribution, that second term, the regular objective, is going to keep them pinned to their correct values. But for everything that is not seen, everything that's out of distribution, that top term is going to push it down, so you will not think that actions that are too different from the ones in your training data are better than they really are. You might think that they're worse than they really are, but that's okay because then you won't take them. Now, there are a lot of ways to improve this method, and there are a lot of ways to do better in allowing the model to extrapolate a little bit, but not so far that it gets into trouble. And striking that balance is actually important for good performance, but that's the high-level idea. There's some provable guarantees that go with this method. You can actually prove that if you select your regularizer appropriately, then you will guarantee that you will eliminate overestimation. But for practical purposes, the important thing is to make sure we set this up correctly and run it on the right data set to get good behaviors. I'll walk through a particular application that I think illustrates some of these ideas, maybe harkening back to this notion of offline pre-training on large data sets and then fine-tuning, utilizing this conservative Q-learning algorithm. So we ran an experiment on Atari games. Atari games are a very popular benchmark for reinforcement learning, but with a twist where we trained one model on 40 different Atari games to kind of represent a little bit of that offline pre-training that I mentioned with a space exploration robot. There is a Space Invaders game, not the same as exploring another planet, but maybe a good enough proxy to get us started. So we're going to train one neural network with different heads for different Atari games on offline data from suboptimal play on 40 of these different games. Now, at that point, we could test how well this model does on those games, and it does decently well. So the pink bar on the right there is the complete conservative Q-learning method. The other bars are different baseline methods. The dotted black line is the average performance in the data set. So running offline RL does, in fact, do better than the average behavior in the data set. That's good. We're not just copying the data. We're actually doing better. But the important thing, of course, is if we take this offline pre-trained model and then apply it to learn other games. So for example, we can fine-tune to a new game with a little bit of offline data on that new game. And the performance of this method, shown in pink on the left side, is significantly better than, for example, learning from scratch. So the orange bar, third one from the left, that shows the same exact architecture but trained from scratch on the new game. And in almost all the cases, actually pre-training on those 40 Atari games allows you to do significantly better when you're fine-tuning to a new game. You can also fine-tune from online experience. So you can actually learn to play a new game more quickly through online experience after this offline pre-training. And again, the pink bar is showing what happens if you pre-train. The cyan bar on the far right is the learning from scratch with regular DQN. The orange one, second from the left, is the same exact architecture learning from scratch. So again, pre-training actually helps quite a lot. And this kind of offline RL pre-training gives you sort of a general prior about what it's like to play video games. So not quite space exploration yet, but has some of those algorithmic elements. Now, there have been many applications of offline RL and conservative Q-learning in particular, some of which I'll talk about today in robotics and dialogue systems, but also in other domains like, for example, mobile notifications, optimizing notification policies so that users are more likely to receive notifications they'll actually click on. It's a great application of offline RL because you can gather lots of data from users, and then you can optimize using that data to get a better strategy. Digital management systems, optimizing agreement conversion, all this sort of stuff. So there's been quite a bit of work that utilizes offline data sets in this way, and I think the best there is probably yet to come. But what I want to talk about next is some of the applications of these ideas and how that can connect to the kind of state-of-the-art AI systems in generative AI that we might be familiar with. So I'll talk a little bit about offline RL and language models, and then I'll conclude with a discussion of how some of these ideas can translate into robotics. So for language models, conventionally, the techniques for training language models, they basically look a lot like what we call imitation learning, where you take data and you train the model to basically output the future tokens in that data and hopefully emulate human behavior. But what if you have a large corpus of data of human-human interactions that are maybe not very good, and you'd like to distill from that data an agent that is more capable of solving that task? Maybe you want to do tech support, and you get something like the Ubuntu Dialog corpus, which is people trying to do tech support. Now, emphasis here is on trying. Sometimes they're doing it successfully. Sometimes they say, oh, why don't you kill all your processes and see if that solves your problem? And then they laugh at you when you actually do it. OK, so people on the internet can have a sense of humor, but our goal is not to have a sense of humor. Our goal is to actually find a better agent for solving these tech support tasks. So can we take a data set of these interactions, which in principle contains a lot of data both about how to do tech support and also how humans will react to different behavior, put it into some kind of algorithm, use it to train a better language model for this task, and then have it actually interact with humans in a more capable way than a standard language model, than a standard LLM. Just copying humans doesn't lead to great performance because humans themselves aren't necessarily great at this task. Humans might be very good in aggregate at exploring the design space of possible behaviors, but perhaps no single human is particularly exceptional here. The data does tell us a lot about how humans will respond to different behaviors. So how can we leverage these patterns to do better than humans? So let's try to frame this problem as a reinforcement learning problem. I'm going to use this example of the visual dialogue task that was introduced in a paper by Das et al., where you have a questioner and an answerer. The agent controls the questioner, and the questioner is supposed to ask questions and then guess which picture they had in mind. So it's like a game of 20 questions, only more open-ended. So we can say that every utterance that is generated by the human or by the environment, by somebody other than our agent, is an observation that it gets to observe, and it can act based on that observation. Everything that the agent says is an action. And the dialogue consists of alternating observations and actions. So the action is what the bot says. The observation is what the human says. The state is your history. If you concatenate your entire history, you know where you are in the conversation. And the reward depends on the outcome of the dialogue. So here the goal is to guess the right picture. So if at the end you guess the correct picture, then you get a reward. In tech support, if you solve someone's tech support problem, at the end you get a reward. Now, this is not the same as RLHF. Many of you might be familiar with RLHF for language models. Very different setup. In RLHF, the goal is to learn from human preferences that humans actually express about which utterance is better or worse. Here, the goal is to learn from dialogue outcome, the actual result of what you said. A human looking at what you said might not be able to tell a priori whether you said something good or not. You can only tell whether it was good or not by the outcome at the end when the conversation actually concludes. An episode in RLHF is typically a single utterance. So the goal is to look at a single thing that the bot says and express a preference whether it's better or worse than another utterance. Here, an episode is an entire dialogue and involves actual interaction with somebody else. So here's an example method that can allow us to use offline RL to optimize these kinds of agents from dialogue data sets. This is a method called implicit language Q-learning, or ILQL, but there are other methods that could be formulated in an analogous way. So we're going to put offline RL in this box, and in particular, we're going to put in a Q-learning based method. We're not going to actually treat every single utterance as an action. We'll actually treat every single token as an action. Now, that's a generalization because if you outputted a token and it's still your turn, then you get to pick the next token. But if you outputted the last token, the end of sentence token for your utterance, then the other person gets to go, and then the next two tokens are out of your control. So it's a generalization of the original formulation. And let's say that we're going to pretend that words are tokens. I know that words are not tokens, that tokens are a little bit more nuanced than that. But for simplicity, we'll say that words are tokens. So here's the tokenization of that utterance. This is the one that you're producing. And this is going to go into a transformer value function. It looks a lot like a language model, transformer self-attention that everybody knows and loves. And instead of outputting a likelihood over the possible tokens at each position, what this model is going to output is a Q function over tokens at each position. Remember, tokens are actions now, so every token that you could output has a Q value associated with it. It's still a number, so it still looks a lot like the likelihoods out of a regular language model. The number just means something different. So in particular, the loss function is going to take these numbers and is going to compute the right-hand side of the Bellman equation, which means that for the next token, it'll take its estimated Q values, take the max over those, and add the reward. Now, the reward in most of these tasks only appears at the end of the conversation, so the reward is usually 0 unless you're on the very last token, in which case the reward is the outcome for the entire dialogue, and that's the target value in the loss function. So structurally, this looks a lot like training a regular language model, just with a different loss function. And the numbers here don't sum up to 1, of course, because they're not probabilities anymore, or at least they're not probability distributions over the tokens. It turns out that if your rewards are 0 and 1, the numbers are still probabilities. They just mean something else. So in a regular language model, the probability is the likelihood of the next token given the previous tokens. Here, the numbers are the probability of succeeding at the task. If your reward is 1, that means you succeed. 0 means you fail. So the expected value of that indicator is the probability of succeeding given the word so far and the new word that you are choosing. So it's still a probability, but it no longer sums up to 1 over these things. Practically speaking, when you go to implement this, it's actually not all that different from regular supervised learning of language models, but with a different loss function and a few details to stabilize this training process. OK, so here are some example generations on this visual dialogue task. Unfortunately, this task is not all that interesting. I'll show more interesting tasks a little bit later. But with a standard reward function that just rewards the agent for guessing correctly, it asks kind of reasonable questions. So the green one, the questioner is the bot. It says like, oh, is the man young? Is he wearing glasses, et cetera? OK, kind of what you'd expect from a game of 20 questions. But now, using the same data, you can go in and you can mess with the reward function. For example, one of the things we did is we changed the reward so that the agent gets a penalty if the answerer answers with yes or no. Now, this is not a penalty for what the bot said. This is a penalty for the answer that it got. So that incentivizes it to ask more nuanced questions like, what color is the kite? And you can have an even more strict penalty that says, well, as long as the answer is not detailed like a number or a color, then bad stuff happens. So then you ask even more intricate questions. Not a particularly useful thing, but a nice proof of concept that with the same exact data but a different reward function, the offline RL method leads to qualitatively different behaviors. But after we did this work, we kind of realized that getting a lot of dialogue data in a particular domain is actually kind of hard. You could do it if you're like OpenAI and you have your chatbot talking to millions of humans on the internet. But for us as researchers, we didn't have that. So we thought, well, can we actually use some of these ideas to get better dialogue maybe even without any good data. So maybe let's say that we want an agent that will be a good teacher. So somebody asks, oh, can you teach me about behavior cloning? And instead of just spitting out a huge instruction manual the way that GPT-4 would, it actually starts asking questions. Of course, I'd be happy to help. To start with, could you tell me if you've ever come across the term artificial intelligence before to like gauge your level of proficiency to tailor the answer appropriately? Well, of course, if you type this into like ChatGPT, you get a single answer. And that single answer is very detailed, but it's kind of a one-size-fits-all answer. And it makes sense because this model is trained so that each utterance is maximally aligned with human preferences. Those preferences aren't looking for what happens if a human responds and then you follow up. They just want this one utterance to be perfect. We're going to want the dialogue agent to be better so that the outcome of the conversation at the very end is what we want. And we want to do this without having to generate lots of dialogues from real humans. So what we're going to do is we're going to generate lots of dialogues from language models. We're going to ask those language models to pretend to be humans and to pretend to be teachers and generate fake data and then run RL on that data. So a person comes along and says, make me a dialogue agent that can teach people about behavior cloning, ask clarifying questions. That goes into a big language model, which generates fake interactions between students and teachers. Crucially, this data doesn't have to be data of good teachers. It has to be realistic in the sense that the student needs to respond to the teacher in realistic ways, but the teacher doesn't have to be a very good teacher for this to work. In fact, it's actually better if the teacher is a highly randomized teacher, because that produces our data set, and then we're going to run RL on that data set. So the data set is not a data set of how a teacher should act. It's a data set of how a teacher could act and the responses that they will get if they do that. And then RL can go in and say, like, OK, now I know that if I say these and these things, these good outcomes will result. So then the RL process can produce a much better teacher from looking through this data set. And the key insight here is that RL with language models is great for tasks that are easy for LLMs to simulate, but hard for them to perform optimally. So the optimality comes from RL, and the generation just needs to simulate lots of plausible outcomes. So with RL, instead of emulating humans, LLMs can learn to achieve desired outcomes using their understanding of how humans would behave. And that's exactly what we wanted from the very beginning from this offline RL recipe. So you can call this a model-based offline RL technique. Here's a comparison of an actual conversation. This is the GPT-4 baseline. So here a person comes along and says, I've been hearing about something called behavior cloning, but I don't really know what it is. Can you explain it to me? And it gives these like fairly long-winded answers. Here the prompt actually very carefully was designed to prevent long-winded answers. So if you just naively ask this, you'll get an even more long-winded thing. This basically told it to be concise and ask clarifying questions. And then here's our agent. The answers here are much more concise, and they really lead towards a particular outcome. So in response to that second question, it says, well, no problem at all. Let's take it step by step. Have you ever used a computer or a smartphone? So these kinds of prompts basically get the human to explain their level of proficiency, and then the agent can respond in more informative ways in a more interactive setting. OK, so that's how data and optimization come together to give us more capable agents for language models. But now let's bring this back to the physical world. So the language model isn't going to go and explore another planet for us. Let's talk about systems that perhaps could. If we want to design effective robotic foundation models, general purpose robotic models that could be used to pre-train things like our space exploration robot, we need to get several things right besides just the algorithms. We need large-scale robotic data sets. We need, of course, the algorithm foundations. And then we also need flexible and general models. And if we can combine all of these things, then we can perhaps get general purpose pre-training techniques for robots that can allow for things like that space exploration robot. So since I've talked a lot about algorithms already, I wanted to focus more on the other parts of this problem for the robotics section of the talk. We've been working on robotic foundation models for navigation quite a bit, and one of the ways that we could approach this is by actually pooling data from many different robotic systems. So we thought, well, could we build a general navigational system with these kinds of ideas? We gathered all sorts of different robotic navigation data sets from the web for vehicles ranging in size from small-scale RC cars to full-scale ATVs. And we trained a very simple policy from this data set. This policy is not actually even trying to optimize any particular task reward function. It's actually just trying to reach goals. So you can think of it as a very general universal reward function where the agent receives a reward if it reaches an image that matches a goal image. And so this is very convenient to train from offline data. And we trained on all the data from all these different robots. The only modification to handle multiple different robots was to just feed a little context, basically a little history into the policy, which it can use to infer what type of robot it's controlling. And it turns out that the resulting policy not only can control the 6 robots in the training set, but it can also generalize to new robotic embodiments. So for example, it can fly a drone through a hallway. Now, for full disclosure, the drone is pretending to be a car in the sense that it's flying at a constant altitude. But besides this, it has different dynamics, different camera properties, and so on. And the model has never seen drones in the training data. The training data consists entirely of ground robots. But the drone actually flies through hallways successfully. We can extend this to larger models, so getting the architecture right is actually really important if you want something scalable and generalizable. So more recently, we developed what we call the visual navigation transformer, which is a large-scale transformer-based model. This model can generalize even more broadly to other embodiments, including quadrupedal robots. We can even do a little bit of prompt tuning with this, automated prompt tuning with this model, where we can take the part of the model that encodes the goal, replace it with another little network that encodes a different type of task representation, like turn-by-turn instructions, turn left, turn right, or go straight. And then we can fine-tune it, for example, to drive a simulated vehicle in the carless simulator. So the model is pre-trained on lots of real-world data for reaching goal images, but then fine-tuned for turn-by-turn instructions, like in Google Maps, in the carless simulator. And that actually also works. We can also take this model to a variety of real-world settings. We can also release it online, and actually people have taken this model and used it for all sorts of settings. What you can see there, the little forest video that is, I believe, in Estonia, where someone used this model for an orienteering task where it drives a robot through a forest. In the bottom left, that's, I believe, in Finland, where there was a group that was studying semantic navigation using the visual navigation transformer as the low-level navigation policy. So there are a lot of applications of this that people can just grab the weights directly and use them. We've also demonstrated ourselves at various conferences. It can navigate around humans. What we didn't tell people is we never actually trained the model around humans. We did train in a lot of forests, though. So humans maybe look a little bit like trees. So as long as they don't move too fast, the model does a good job. Now, taking this back to our space exploration example, we can actually initialize from multi-robot data and then fine-tune with online RL for new tasks. In this case, the task is to race as quickly as possible around the Soda Hall 5th floor. Hopefully nobody here is works in Soda Hall 5th floor. If you do, please, I'm sorry about the robot running into you. But what we did here is we took the GNM data set, the one that was used in the work from before. We ran offline RL pre-training on it, and then we fine-tuned from that model with online RL through real-world experience. Now, initially, the robot doesn't do very well. But after just 15 minutes of training, it starts actually getting the idea. So it still bumps into the walls a little bit, but it goes around the hallway kind of OK. And after a total of 25 minutes, it can actually race around the hallway at speeds comparable to what the expert human driver, the graduate student running this experiment, could do using the first-person camera. Now, to me, this is actually quite remarkable, because 25 minutes is a very short training period for an RL algorithm that is controlling a robot directly from image pixels. Of course, the model is not trained from scratch. Crucially, it is pre-trained on that offline data from other robots. And I think this is a really nice illustration of that principle from before, that if you have the right pre-training approach to bring in that prior knowledge, those general navigational priors about how the world will move around you, then you can run RL very quickly and adapt and find novel solutions to novel situations. Here's the same system after it trained outdoors. Outdoors, it learned this interesting behavior where if it goes on the paved path, it can go a little faster. The checkpoints are located on the grass, so it has to cut onto the grass in between the checkpoints, but it'll go back onto the path once it is able to do so. And here's the first-person view. The first-person view, I think, nicely illustrates this is actually a fairly non-trivial task with so much shaking and occlusion and things like that. OK, now that's for navigation, and we might argue that navigation is maybe not the most complex problem, because mechanically it's not that bad. The number of degrees of freedom is small. Can we do the same thing for robotic manipulation? Recently, we worked with a pretty large group of collaborators to study this question. This was a collaboration between a number of research institutions as well as Google Research, led by Quan Vuong and Carl Perch, where what we did is we contacted 34 different academic research labs that were studying robotic manipulation, and we asked them to donate their data sets to us, donate in the name of science, so that we could train one model across all of these data sets to see if we could achieve a kind of general purpose robotic manipulation prior. There were 22 different robots in this data set and about 1 million total trials. And to get a sense for what the data set looks like, it helps to see the variability in the example. So everything ranging from robots routing cables to opening trash bins with a stretch robot. A lot of variability, a lot of different systems. And if we train a single policy across all of these different robotic systems, we can then send that policy to some of the labs that donate their data set and ask them to compare it to whatever model they had, whatever they were developing for their own tasks. Now, this is a very difficult test because in robotics, if you're developing a new method for a particular task, chances are your method is a pretty good fit for the task that you're developing. So if someone else sends you their model, it's pretty tough for them to compete. Turns out that this general model trained across all these different robots on average performed about 50% better than the best method each lab had for that task. So the rainbow colored bar here is this cross-embodiment model. And that to me is actually pretty interesting because this suggests that the generalist model is actually outperforming specialists in the individual domains where those specialists are trained. And that's, of course, something that we've seen with language models where they outperform more specialized NLP systems, but it's not something that has been seen very much in robotic learning. So to summarize, you can imagine a kind of a general robotic model recipe where you take all the data from all the different robots you've seen before, you use it in a kind of self-supervised offline RL recipe where you learn to achieve goals or you learn to achieve a general range of tasks, and then you can fine-tune from that model to a variety of settings, including new embodiments, new types of task modalities, fine-tune with RL for racing around a hallway, and other kinds of tasks. And that might be a way to instantiate that notional recipe from earlier with a space exploration robot. Okay, so what have we done and what remains open? Well, robotic learning from multi-robot datasets seems to work and enables robots that people around the world can use. Offline RL can enable more performant policies and can enable rapid online RL fine-tuning. This seems to hold for both navigation and manipulation. And the largest models heavily use imitation learning, and integrating all the components is yet to be done. So there's a lot more advances that we need in scalable RL and scalable offline RL, but I think we're getting there. To just conclude this talk, I want to finish with a very brief discussion of something that many of you might have heard of, but might not realize how it relates to the topic I'm talking about. So some of you might have heard about an essay by Richard Sutton called A Bitter Lesson, which is a very nice, concise exposition of more or less the principles underlying the current wave of large-scale machine learning. And one of the quotes from that essay, which I have here, says, "We have to learn the bitter lesson that building in how we think does not work in the long run. The two methods that seem to scale arbitrarily are learning and search." A lot of people read this essay and think that what it really means is that we need to shovel more data into GPUs, and that really methods, algorithms don't really matter so much as our ability to build large-scale machine learning systems. There is some truth to that, but there is an important nuance that Richard Sutton gets across in this essay that I think people sometimes miss. And that's in these two words, learning and search. The words are a little bit loaded, and they're maybe a little bit of technical jargon. But what they basically mean is this. Learning is the use of data to extract patterns. You go out into the world, you fetch data, you use that data to find patterns that exist in the world. Search is not about the data. Search is about computation. It's about using computation to extract inferences. You take what you learn, and you analyze it to find better strategies, to search for better solutions to your problem. It's some optimization process that uses typically iterative computation to make rational decisions. And learning is what allows us to understand the world. Search is what leverages that understanding for emergence. And we really need both of these things, because data without optimization doesn't allow us to solve new problems in new ways, and optimization without data is hard to apply to the real world outside of simulators. But if we put these two things together, we can have data-driven agents that outperform the best that humans can do on any given problem. Thank you very much for listening. I'll be happy to take questions.
Thank you very, very much, Sergey, for that fascinating talk, and very much in the spirit of the conference. And so I think what I'd like to do is call Dee up to start setting up her laptop, and in the spirit of asking succinct and meaningful questions and responses, does anyone have a succinct but meaningful question for Sergey? Just wait for the microphone, and then, yeah, perfect. Thank you.
Thank you, Professor. I have a question about the next step about the incorporating video generation with model-based RL, because with the SORA things going on, and people in the RL community are trying to use RL, use video generation with search, with actually planning and search in the to try to improve in the model-based RL. So I want to see your opinion on what's the next step to how do we incorporate those word simulator things into the model-based RL research.
Yeah, that's a really good question. Well, and I'll say that the dialogue agents work I discussed actually had a lot of elements of that. It had elements of synthetic data generation as a way to augment data sets for reinforcement learning. I think one of the delicate things about doing model-based RL at a large scale is that it's kind of easy to get models, comparatively easy to get models that are sort of qualitatively right, but it's very hard to get models that are right in all of the details. So it's very tempting to think of models, especially video prediction models, as essentially learned simulators. In the same way that you can have like a good physics simulator, you can use a learned model, use it to generate lots of very high fidelity data, and then learn on that data. But in practice, I think it's, at least so far, it's proven to be very important to adopt the right kind of abstractions. When you have models that can kind of get the gist of something right, like they can get the gist that, if you open a door, then you can go through the door. But they might not get the details right that, this is how you have to hold the handle in order to turn the handle. So accounting for those flaws and building a system that combines model-free and model-based reasoning in the right way, where the model-free reasoning can sort of fill in the details where the model might not be entirely reliable, in practice turns out to be really important to make that work. Now, I don't know if that will remain the case going forward. Like maybe generative models just get so good that we can use them to simulate, and that's great. Like that's a really good way to build model-based offline RL methods. Or maybe we'll always need some kind of interplay of these two elements. So I'm not sure. Remains to be seen.
OK, thank you very much. Thank you for the question. Thank you again, Sergey.